Welcome back to quadratic equations. In our previous lesson, we solved the roots of a quadratic equation and we were able to find rational roots, real roots, imaginary roots. For this lesson, our objective would be to determine the nature of roots a given quadratic equation has, even without solving for the quadratic equation. For lesson 3.6, I'm going to split the topic into two. The first one will be the nature of roots. The second one will be sum and product of roots. Our objective for 3.6a would be to determine the nature of roots of a given quadratic equation without solving for the roots. Okay, let's recall the quadratic equation ax squared plus bx plus c equals 0, a not equal to 0, a, b, c element real. We know that the solution to this equation is given by this formula, our quadratic formula. In this quadratic formula, the radicand here is our discriminant. Computing for the discriminant will tell us the nature of the roots of a given quadratic equation even without solving for the roots. Now, what are the possibilities for D? First possibility is D greater than 0. Second is D equals 0. Third is D is less than 0. These are the possible values for the discriminant of any quadratic equation in this standard form. Let's have case number 1, D greater than 0. We may be able to have here, let's say 25 is greater than 0, 19 is greater than 0. But what's the difference between these two? One of them is a perfect square and the other one is not a perfect square. Okay? Looking at this number 1 here, suppose D is greater than 0, then the roots of our quadratic equation are real and unequal. If D is greater than 0, then the roots are real and unequal. But there are two types of D which is greater than 0. Either the D is a perfect square or the D is not a perfect square. Here, let's get the two cases. If D is a perfect square, then our roots are not only real and unequal, but they are also rational. Again, if D is a perfect square, then the roots are also rational, aside from them being real and unequal. Now, what happens if D is not a perfect square? Then the roots are irrational conjugates. So, if D is greater than 0 but not a perfect square, then the roots are irrational conjugates. At the same time, they are real and unequal. Let's illustrate this property. For example, suppose we have x squared minus 5x equals negative 6. For us to solve for the discriminant of this given quadratic equation, we need to transform this quadratic equation into its standard form. Meaning, one side is 0 and the other side is in expanded form like this. Therefore, what we need to do here will be to use addition property. So we get here x squared minus 5x plus 6 equals 0. From this example, we know that a equals 1, b equals negative 5, and c equals 6. Computing for the d, we get b squared minus 4ac, which gives me negative 5 squared minus 4 times 1 times 6. And this gives me 25 minus 24 which is equal to 1. Note here that 1 is greater than 0, and also 1 is a perfect square. So, what do we expect as the nature of the roots of this given equation? According to what we have discussed, if d is greater than 0, then the roots are real and unequal. Furthermore, if d is a perfect square, the roots are also rational. Therefore, for this equation, the nature of its roots are real, unequal, and rational. Now, we can show that the roots are really real, unequal, and rational by checking, and checking means let's solve the roots of the given equation. From this form here, x squared minus 5x plus 6 equals 0, this left-hand side is factorable. So the quickest way to solve for the roots of this equation will be factoring. The factors of this expression are x minus 3 times x minus 2. You check the middle term, negative 3x and negative 2x will give us negative 5x. And from the zero product property, this one means that x minus 3 equals 0 or x minus 2 equals 0. Solving for x here, we get x equals 3 or x equals 2. Look at the roots that we have solved. 3 and 2 are real, they are unequal, and both 3 and 2 are rational numbers. So, another information here is, if the discriminant that you will arrive at is a perfect square, then the given equation is solvable by factoring method. Let's take a look at an example where we are going to have d equals 0 discriminant. Number 2 here is, if d equals 0, then the roots are real and equal. Since 0 is a perfect square, then the roots of an equation with discriminant equal to 0 should also be rational. But instead of mentioning rational, I would just say real and equal. And here we obtain a double root. Illustrating this, we have this example. Suppose I have here 4x squared minus 12x equals negative 9. For us to use this formula, d equals b squared minus 4ac, our equation should be written in its standard form. Okay, so let's have this in its standard form. We get 4x squared minus 12x plus 9 equals 0. From here, I can identify my a, which is 4, b, which is negative 12, and c is equal to 9. Computing for d, I get b squared minus 4ac. Or substituting the values, we get minus 12 squared minus 4 times 4 times 9. Negative 12 squared is 144. 4 times 4, 16 times 9 is also 144. This gives us a discriminant of 0. If d equals 0, then we say that the roots are real and equal, and we have a double root. Okay, so our conclusion here are roots are real, equal, or we have here a double root. Let's find out if this equation indeed will give us roots that are real and equal. Okay, so going back to solving the solution set of this equation, I will now solve this equation on the second row there. So we get 4x squared minus 12x plus 9 equals 0. And I can see that this is factorable on the left hand side, so I will apply factoring method to solve for the solution set of that given equation. In fact, I recognize that 4x squared minus 12x plus 9 is a perfect square trinomial which is factorable as this square of a binomial 2x minus 3. Using the zero product property, I will equate these factors both to 0, and solving for x we get x equals 3 over 2 or x equals 3 over 2. Indeed, we have roots that are real and equal. Of course, they're also rational, but more particularly, we have a double root. Okay? 3 over 2 is a double root. Let's have the last case. The last case, if d is less than 0, then the roots are conjugate complex numbers. For example, suppose we have here 2x squared minus 3x plus 5 equals 0. Solving for the discriminant of this quadratic equation, we have to identify a equals 2, b equals negative 3, and c equals 5. And the formula for the discriminant is d equals b squared minus 4ac. Substituting in this equation here, b is negative 3 squared minus 4 times a is 2 times c is 5. And I get here, negative 3 squared is 9, 5 times 2, 10, times 4 is 40. We have a negative 40. So we have 9 minus 40 will give me negative 31. Note that negative 31 is less than 0. From this property, our roots are conjugate complex numbers. Okay, let's show if the roots are really conjugate complex numbers by solving for the solution set of this equation. Note here that 2x squared minus 3x plus 5 is not factorable. So this quadratic equation may be solved using either completing the square or using the quadratic formula. Here, it's convenient for us to use the quadratic formula where a equals 2, b equals negative 3, and c equals 5. Substituting in the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a, we have the following. Negative of negative 3 plus or minus square root of b squared is negative 3 squared minus 4 times a, which is 2, times c, which is 5, all over 2 times 2. And I have 3 plus or minus square root of 9 minus 40 all over 4, which gives me 3 plus or minus square root of negative 31 all over 4. Let's find out how to simplify square root of negative 31. Remember before that if we have a square root of a negative number, we are going to express that negative as negative 1 separately there. But negative 1 here is actually I squared if the index is even. So simplifying this, I have perfect square I squared will give me now I square root of 31. Therefore, I can write my solution as 3 plus or minus I times the square root of 31 all over 4. Now, what kind of roots do we have here? We have conjugate complex numbers. Conjugate to mean if we have 3 plus I squared of 31, then its conjugate should also be a root, which is 3 minus I squared of 31 over 4. Okay? So, to summarize, there are 3 possible values for this discriminant of a quadratic equation. First, D is greater than 0. Second, D equals 0. Third, D less than 0. And we said that if D is greater than 0, the roots are real and unequal. If D equals 0, the roots are real and equal. If D is less than 0, the roots are conjugate complex numbers. Furthermore, if D is greater than 0 and D is a perfect square, then the roots are also rational. If D is not a perfect square, then the roots are irrational conjugates. If D equals 0, we have a double root. Also, if D equals 0 or D greater than 0 and a perfect square, the quadratic equation is factorable. Thank you.